Welcome to The Explainer. Today, we're taking a deep dive into something that literally surrounds us every single second of our lives, and that is heat and energy. Now, sure, this covers some core principles of physics, but honestly, it's really just the fundamental science of our everyday reality. I mean, ever catch yourself wondering why a metal spoon becomes instantly hot when you leave it in a fresh cup of tea? Or why, on a crisp morning, just stepping into a patch of sunlight instantly makes your skin feel warm? These are super common everyday mysteries, but the answers are entirely rooted in the fascinating science of heat and energy. So today, we're going to embark on a little journey, starting from the massive, macro world we can see, all the way down to the invisible, microscopic behavior of particles. Okay, let's dive right into this. Here's our roadmap for today. First, we'll look at heat versus temperature. Second, energy and its forms. Third, how heat travels. Fourth, the power of specific heat. And finally, expansion and other effects. Section 1. Heat versus temperature. We're going to start by busting the biggest physics misconception out there. So, a lot of people use the words heat and temperature interchangeably in daily conversation, right? But let's define heat first. Heat is, quite simply, a form of energy. But it has a very specific behavioral rule. It's energy that flows from a hotter object to a colder object, purely because there's a difference in temperature. Think about it. If you set a steaming hot cup of coffee on your kitchen table, you know it doesn't stay hot forever. Heat energy is actively flowing from that hot coffee out into the cooler air of the room. And that flow continues until the coffee and the room reach the exact same temperature. Oh, and because heat is energy, we measure it in joules. Let's actually look at these two side by side to clear things up. The crucial takeaway here is this. Heat is flowing energy, measured in joules. Temperature, on the other hand, completely different. It's a measurement of how hot or cold an object is, sure, but scientifically speaking, it indicates the average kinetic energy of the microscopic particles inside a substance. And we measure that with a thermometer, usually in Kelvin or Celsius. So when you're taking a temperature, you aren't actually measuring the flow of energy. You're literally measuring how fast those invisible particles are jiggling around inside. Moving on to Section 2, energy and its forms. Let's talk about the capacity to do work. At its core, physics defines energy in a beautifully simple way. It's just the capacity to do work. And energy isn't just one single thing. It exists in a bunch of really dynamic forms. We've got heat energy, of course, but there's also light energy illuminating our world, sound energy carrying my voice to you right now, electrical energy powering your device, mechanical energy which involves physical movement, and chemical energies stored inside the bonds of molecules. Heat is really just one vital piece of this much larger puzzle. But here is probably the most profound rule governing all these forms, the law of conservation of energy. It states that energy can absolutely never be created and it can never be destroyed, period. It merely changes its disguise, transforming from one form to another. Take a standard electric heater. It isn't magically creating heat out of thin air. It's actually taking electrical energy from your wall outlet and transforming it entirely into heat energy. The total amount of energy in the universe always remains perfectly constant. All right, Section 3, how heat travels. We're looking at the 3 methods of heat transfer. Now, what's really interesting about this is how heat actually moves. There are 3 distinct methods. First up, conduction. This requires direct physical contact and happens primarily in solids. Remember that metal spoon in the hot tea? The particles in the spoon don't actually change locations, they just vibrate and pass the heat along. Metals are fantastic conductors, while stuff like wood and plastic are pretty poor ones. Next is convection, which happens mostly in liquids and gases. Here, the particles actually do move. When you heat water in a pot, the water at the bottom gets hot. It rises and the colder water sinks, forming continuous convection currents. Finally, we have radiation. This one's wild because it transfers heat without any medium at all. It literally travels through the empty vacuum of space. That's exactly how the sun's heat reaches us here on Earth. Oh, and a quick tip, dark-colored objects actually absorb this radiated heat much faster than light-colored ones. Section 4, the power of specific heat. Let's talk about water's stubborn superpower. To really understand this superpower, let's anchor it with a strict scientific definition. Specific heat capacity is a highly precise measurement. It is the exact amount of heat energy required to raise the temperature of exactly 1 kilogram of a given substance by exactly 1 degree Celsius. And here is where it gets super fascinating. Water has a highly elevated specific heat capacity, but what does that actually mean for you practically? Well, it basically means water is incredibly stubborn about changing its temperature. It requires a massive amount of heat energy just to warm up. That's exactly why waiting for a pot of water to boil on the stove feels like it takes an absolute eternity. But the flip side is true too. It cools down very slowly, holding onto all that thermal energy for a really long time. Finally, Section 5, Expansion and Other Effects. Here's what heat actually does to matter. Let's zoom back out to the macro scale for a second. When we introduce heat energy into a substance, it triggers some pretty major physical changes. First, as we know, it increases the temperature. Second, it can completely change the state of matter. And third, it causes the physical expansion of substances, whether we're talking about solids, liquids, or gases. Why does this happen? Well, because when substances are heated, their internal particles move faster and literally spread further apart. Just think about a basic change in state. As heat energy is continuously added, a solid block of ice transforms into liquid water. Keep adding more heat, and those particles spread even further apart until it becomes a gas, steam. That entire transformation is completely driven by heat energy. And this brilliantly illustrates why understanding this microscopic particle movement matters on a massive, real-world scale. Think about railway engineering. Railway tracks are actually built with intentional gaps between those huge solid metal rails. Why? Well, because during the hot summer months, the metal absorbs heat, the particles move faster, and the solid material undergoes physical expansion. If engineers didn't leave those gaps to allow for that expansion, the tracks would literally buckle under the immense pressure. So we've covered a tremendous amount today, from convection currents to the unbreakable laws of energy. I want to leave you with one final provocative thought. Just look around the room you're in right now. Based on the law of conservation of energy, we know energy is never destroyed. It merely changes form. So where is energy transforming in your space right at this very moment? And where is that energy eventually going to go next? Keep viewing the world through the eyes of a physicist, study smart, and keep learning.